policies in the DHCP server. You can try with it at home if you have an ADSL modem. You can decide, for example, that some MAC addresses may have some IP addresses. So you may decide that some of your machines will always have a well-known address. For example, that's typically done for easing the configuration of printers or things like this. So that, and of course you can have very sophisticated DHCP servers in large enterprises that may have policies that might forbid some MAC addresses. So you might need to declare a MAC address in advance. So the DHCP server typically remembers all of the MAC addresses. With IPv6, as you can imagine, is the same but more complex. In fact, DHCP was invented for IPv6, and then it was retrofitted to IPv4. So it's exactly the same, with the usual differences that we refuse broadcast. So instead of sending the request, which is also called differently, is a solicit, it is sent, it is not broadcast, but it is sent to a reserved multicast address which contains all DHCP relay or servers. So this specific IPv6 destination address means anybody who has a DHCP server or DHCP relay function. So similar to what the same trick as we saw before, it's an attempt to hope that only few machines will get it. A few other differences is that we don't use either the 00 address, but the 0 address scope to local link. So this prefix means that this is a local link address. A local link address, remember, they exist for IPv4 and IPv6. In IPv4, they are on the 169 dot something. In IPv6, they are those prefix, FE80. Link local means it's an address that has a meaning inside a local area network only. One could say it's completely useless because inside the local area network, if we put 0, then we have the MAC address that could help to get it. That's how IPv6 does it. IPv6 is trying to get rid of the MAC layer. So in the future, it is in 20 years, say, when IPv6 is widespread, it is possible that the MAC layer disappears. And then this course will be simpler, but I will be retired. The allocation of the IP addresses in IPv4 is usually relatively simple because in IPv4 you don't have many addresses. So if you sit in one part of EPFL, 24 bits of your address are dictated by where you're connected, and then you have only 8 bits to choose, so the DHCP will not have a lot of choice. For IPv6, you have more choice at EPFL. The prefix is 64 bits, so you have an entire set of 64 bits to give the IPv6 host part. So some systems can be smart, like the EPFL DHCP v6 system. It has decided things that are shown here. Here is the address I get when I sit in my office, here. And you recognize perhaps, so it is made of 4 blocks of 16 bits. The first block is always 1, and the last one is always 1. So that means that's the first IPv6 numbering plan of EPFL. And the red part, the part in between, is the same as the IPv4 address. Now it's coded in hexadecimal instead of dotted decimal, but this is exactly the same as I will get from my IPv4 address. That's a way that's very specific to EPFL and to places like EPFL, where we have both IPv4 and IPv6. So in order to simplify the network management, they've decided to give the same IPv6, to give inside the IPv6 address the IPv4 address. So now if somebody is doing something bad, like peer-to-peer transfer of high volume, then you can immediately find who it is, and you don't have IPv6 address that would be different from IPv4. That's very typical of places that have the luxury of having both IPv4 and IPv6, which are typically universities. Because if you have the luxury of having both, that means you don't need IPv6 because you have enough addresses. So if you still do it when you don't need it, that means you're a university or a research center or something like this. If you're a bank, you don't, because it costs money to deploy IPv6. Okay, I'll skip the next quiz. DHCP is the classical protocol used for allocating addresses. There are other ones that are less visible, but if you're curious, if you try to go to your ADSL modem, which itself is seen by Swisscom or Sunrise or Cablecom as a host, it will get its IP address automatically from the other end of the line. And here the protocol has a different name. It's not called DHCP, it's called PPP, point-to-point protocol. But morally speaking, it's the same as DHCP, but it's typically done over telephone lines. I'll skip the details, but you can look up Wikipedia to understand the details. Now in IPv6, things are a bit more complicated as usual, because people thought to do things more simple, and then at the end, it's more complicated. The simplicity was trying to imitate AppleTalk. In the 90s, if you would buy a Macintosh, 2 Macintoshes and 1 printer, you connect them together with AppleTalk wires, which were like low-grade Ethernet wires. They automatically connect to each other, which means they get their addresses. It was not IP addresses, it was AppleTalk addressing information, but for us, morally speaking, it's the same as IP. And they would get that automatically. Right? And then it's called the plug-and-play feature, or the dentist's office scenario. Right? You have a number of devices that are not connected to the public internet, so you want them to get their addresses automatically. And in IPv6, the idea was to do the same thing. I connect a box, it should get its IPv6 address automatically, and there is a protocol for that which is called SLAC, Stateless Address Auto-Configuration. I'll explain why it is stateless. The idea is very simple. We'll look at the details, and as usual in IPv6, they're complex because we need to analyze the bytes and bits of the addresses. But the idea is very simple. The idea is, I am an IPv6 host. I want to have an address. Well, if things are like in most cases, the host part will be 64 bits. In 64 bits, I can put my MAC address. There's enough space. So for the host part, I will have an algorithm to automatically give the host part based on my MAC address. And for the network prefix, well, the network prefix, there are 2 possible cases. Either I am in a dentist's office, a dentist of the 90s, not connected to the internet. Then I need any prefix that is, in fact, I can even use the link local prefix FE80, sorry. So if there is no router, I can use this prefix. How can I know if there is no router? Well, by sending a question to the multicast address of all routers, who is a router in my LAN? If somebody is a router, if no one is a router, I will know, and I will use the link local address, and I have my IP address, and the dentist's office scenario works. If there is a router, or several, then they will respond to me with a prefix. If you are a router, you know what is the subnet prefix on each of your interfaces. That's part of the configuration of a router, of what is the routing protocol that we will see in Lab 4. You will play with those configurations. So the router knows, then it can respond to me, here is the prefix, then I get the prefix, I get the host part, I get my IP full address. That's the idea of SLAC. So this is how it works. And then as usual, you find those funny IPv6 stuff. You avoid broadcast by using solicited node multicast address. So first, when an IPv6 host boots, it always gets its link local address. I said we will use link local address if the others don't work. In fact, we always have them. So a link local address is an address that starts with this prefix. You add, for example, depending on how your operating system is configured, you add your MAC address and the host part. How do you go from 48 to 64? We'll see in a few minutes. And then you still do a duplicate test. If you would be in IPv4, a duplicate test consists in sending a broadcast to everyone saying, here I am, here is my IP address. If you're in IPv6, you don't broadcast. You send to the solicited node multicast address of this address that you're trying to acquire. So you will bother only the nodes that do have the same address as you, which hopefully is nobody. So if nobody has it, nobody will receive this packet. And if that works, that means if you get no reply, you get this address. So you already have an IP address, which is already advancing in your life. How do you get this host part derived from the MAC address? In fact, you've seen that in the lab already. There is a very clumsy way of flipping the bits that I'll skip here, but you can see in detail. If you have this MAC address, at the end you will get this host part, where you've essentially added FFFE in the middle, and you've changed one bit, the bit number 7, for reasons that are a bit too long to explain, or not. Bit 7 is equal to 1. The bit 7 of a host part allocated in this sense is a bit that keeps a trace of whether this address is locally assigned or globally assigned. Locally assigned means assigned by somebody who decided to give this host part, or globally means it's really from the hardware address that is in your Ethernet or Wi-Fi adapter that has been given to Apple or to whoever. That's global. And local is, for example, an address like EPFL that decides your host part doesn't come from this MAC address, but comes from the address that we, EPFL system managers, decided to give to you, which is derived from our IPv4 address. And one of the rules says bit 7 should be different in both cases. So as you see, there's lots of funny things in IP addressing. I mean, when you sum up all those details, we don't necessarily need to dive into all of them now, but we need to know that they exist. Now, some people don't like this address, so some operating systems do that. But Microsoft in particular posted a number of papers saying, but that's not good because there is a problem with that. What's the problem? Well, you can be tracked. If you move from one place to another, you get an IP address. Now, wherever you are, if you do this, the 64 last bits of your IP address are always the same and are your MAC address. Okay, so that was done before, I say at least more than 10 years ago, where people cared about privacy. So I said, well, it's we should obfuscate things a bit. Now you're tracked anyhow if you have an iPhone or an Android phone by all the data that your Android or iPhone sends to Apple whenever you do anything. But if you have a Microsoft thing that perhaps sends less, you would like to have an address that is less trackable. So what Windows machines will do, they will do, and there's another standard for it, so it's another option that you can do, they will compute a random address. Instead of computing a 64-bit address derived from your Mac, they will compute one randomly. Of course, they will do the duplicate address test to see if somebody has the same. As there are many, many bits, the chances that the duplication exists, fails, are very small. And if it happens, you try another random address. And once in a while, and of course you don't keep it forever, otherwise it's like your MAC address. So you need to refresh it once in a while, which means changing the host part of your IP address once in a while. Is it possible? With IPv4, if you do that, it won't work. If you change the IP address of your host, all established communication will break, so you need to reboot everything. With IPv6, in theory, it is envisioned that this should work. In other words, in IPv6, we require that the operating system supports several IP addresses for the same interface. We always have two, in fact. We have the link local address, the FE80, plus we have the globally unique address, if you're not isolated. But in fact, if you use this type of random addresses, you will have a whole zoo of addresses, and the operating system will allow this to happen. And it will, of course, try to get rid of the addresses that are rolled, so it will keep a state. So an IP address, for those systems that use this, has a state which is one of those four here. An address is tentative when you're doing this address allocation. Once you have received it, it is preferred. When it becomes too old, typically after 1 day, it becomes deprecated. But you can still use it, but you cannot establish new TCP connections, for example. Whenever you establish a new thread of code that tries to is not pursuing something that was already cached with a source address, you will not use it. Now, if you have a very, very long TCP connection that lasts for years on your machine, well, you will continue to use a deprecated address. But sooner or later, well, it's very rare that systems live for years. It's only in smart grid and things like this that systems can live for very long in, I would say, the computer world, and you need to reboot a machine if you don't simply change it. So after some time, those flows will die, and you can force the flows to die by having a valid timer that's small, in which case this address will be deleted. That's the way you can protect yourself from being tracked by addresses. And incidentally, we find a concept in IPv6 that you need to remember, that a host typically has several addresses. So, to make this long story short, at the end of this process, the host has one link local address, this one. Then it will do what I mentioned before, which is called router solicitation. So the so-called RS protocol, all used inside ICMP packet. It will send a multicast to this address, which means all routers on link. What does on link mean? In the same local area network. So it means all routers that are in the same local area networks. At TPFL, typically it means one. There's only one if you're at the edge of the router. If you're in the backbone, there might be several. But in the backbone, typically you don't do this. So typically it's one. So that replaces the broadcast. And then the router will see whether it authorizes that type of address allocation. It knows the prefix, the green part, will send it to this host, and then the host has its green addresses. So it knows its prefix. Incidentally, it knows also who is the router, and it can also know who is the default next hop to use to forward to the rest of the world. If we recap at this stage, an IPv6 host has some of its configuration information. Which one? A link local address, and if a router is present, a global unicast address, or if a router is present, a global unicast address and no link local address, or none of the above. I close in 5 seconds. Correct answer 1, of course. This was just. Remember that you can have several addresses, and the link local address is always present. In fact, it's always used by preference. So if for whatever reason you have the choice between two addresses, one of them which would work equally well, one of them is the link local, the other is the global, the IPv6 rules say choose the link local because it's more stable. You might change the numbering plan, but this one is less likely to change. Okay. Unfortunately, so this automatic address allocation, which in the past was said by many that's the main advantage of IPv6, but it doesn't really solve everything. In particular, as we've seen, you need additional information, at least one, which is the DNS address, DNS IP address, DNS server IP address. And if you're a dual stack host, a host that has both IPv4 and IPv6, you may need two, the IPv4 and the IPv6 one. So what could people do? Well, they could decide, let's beef up the Slack protocol and add the DNS server address in it. But that's not what was chosen, probably because it's not a good idea. The Slack protocol that we have just seen, automatic address allocation, is very minimal in sense of information that you need to configure. A router sends out the prefixes it owns, so it knows those prefixes, so there's no additional configuration to be done in routers. And a host chooses its host part independently of the routers, for example, based on its MAC address or a random number generator. So in either case, it's fully plug and play. So in that sense, it's good. Now, if we add DNS into the play, we need to into the story. We could add it in the router, but then it is like putting configuration information into routers that essentially have nothing to do with the information that the router naturally has. So instead of that, the idea is to continue to use DHCP by saying that we can use DHCP even if we use Slack after using Slack. So it's another use of DHCP, where once a host has configured itself and it has an address that works, now you can talk to a DHCP server to get the rest, which is now much easier. You don't need to put a DHCP relay function in the router. All you need is to go to a DHCP server. It's called stateless also because the DHCP server does not allocate the IP address. So it doesn't keep this big table of addresses allocated to whom. It's just like a DNS server. It simply gets a query. Somebody wants to know what's the IP address of the DNS server by default in EPFL, for example, and then it responds always with the same information. It's not completely stateless. It has, of course, the information it wants to respond to, but it doesn't have this big table of MAC and IP addresses that a DHCP server normally has. Voila, that's all the zoo of DHCP. That is very detailed. So that's an example of one of the things that we look in detail because it helps for the labs, and also it gives you a flavor of all the things you need to do to do the things real. There is more in the slides than we will see, but I will invite you to, in particular, try the quiz and see and test your response. I will post the answers tonight. But now I prefer to go to more stuff, in particular on the IP header. If you go to Wikipedia about any protocol, the first thing they will show you is the message format and the IP and the header, etc., which is not what I'm trying to do. As we will see, we see the header at the end. I've tried to go from first principles, and then we should find in the header everything that has to do with our principles. So of course we find in the headers addresses. And then there are other things that we need to discuss. I discussed the next header already, that's the protocol type. That's the name of the protocol type in IPv6. Now what I want to discuss is the hop limit. I'm showing the IPv6 header. A benefit of IPv6 is that the terminology is cleaner. So the header field of interest here, hop limit, is the maximum number of hops that a packet can go through. What does it mean? Well, it means if you're a router, you do minus minus. That means you decrement this field by 1. So when an IP router receives an IP packet, normally it does nothing to the IP packet. You don't touch it. It's like if you're the post office, you have a postcard to send further. You send it further. You don't write on the postcard. Except here you do change one thing, and the one thing you change is the hop limit. You decrement it by 1. The source puts a value which is coded on 8 bits, so it is between 0 and 255. 0 is invalid. If a packet has a hop limit equal to 0, that means it is dead. So you should kill this packet, should do nothing with this packet. And 255 would be extreme. Today, most hosts put a value of 64 or 60, depending on their religion. at the source. What is the effect of this? Why is there a hop limit in IP packets? Yes? If there is a problem in routing, in particular if there's a routing loop, so imagine due to configuration errors or transients, as we will see, the routing protocols whose job it is to do the routing tables properly, they are not synchronized. There's not somebody pushing a button and saying all routing tables in the internet now have the same value. We would be unable to do that because to send the information of the button, we need the routing to work. So we have a chicken and egg problem. So the changes are asynchronous. There may be periods of time where the routing tables are not consistent. If I send a packet to you and you send the packet to someone else who sends it to me, we have a triangle, we have a loop. What happens if there is a loop?
It will not stop, never stop. It will never stop if we don't use the hop limit.
It will never stop, so the packet will never stop. And what happens if a packet never stops? It depends on the propagation versus transmission time. If the propagation time is about the same as the transmission time, one single packet is constantly looping and using all the resources of the loop, right? So with a single packet, you could utilize at 100% a series of links, right? So it is severe. It's a denial of service attack, a wonderful denial of service attack if you manage to make a loop. If the propagation time is larger than the transmission time, then you send a few packets, and a few looping packets will kill any network. So it's very severe. We want to avoid that. We can't avoid it entirely during transients. We can't avoid entirely the loop, so a radical cure is to make sure there is no loop, but we can't avoid it entirely. So in order to avoid that a single packet kills a link, we kill the packet after a number of hops, which is the maximum. So today, if you send a packet with at the source 64, if there's a loop, it will turn a number of times and die. Of course, if a large number of people will do that, the loop might still get congested, but it's better than having the loop completely dead. Yes?
Yeah, is 64 sufficient to go to the other end of the world, like in New Zealand?
Is 64 sufficient to go to the other end of the world? Apparently, yes. Well, we have this law of when you build complex networks that are hierarchical, like the internet. The internet is not hierarchical in the protocols, but in its organization. You have small networks at the periphery, large transit backbones that themselves are connected to larger transit backbones. And typically the depth of organization that are hierarchical grows like log n, where n is the number of devices we have. So today, yes, 64 is sufficient. There's an anecdote when Windows discovered TCP/IP, that was in 1905. The first Windows 95 had TCP/IP natively. They put a TTL of 32 in the packets. And the first demos of Windows 95 in Europe, connecting to servers in California, would not work because there were more than 32 hops. The number of hops tends to decrease. In fact, the internet is becoming a bit flatter because we have the tendency is more to have very, very high-speed backbones that have very, very few hops. So the number of hops, in fact, is more decreasing than increasing. You've used the TTL with Traceroute. This Traceroute uses the TTL. How does Traceroute work? When you do Traceroute and you see the list of intermediate systems, in fact, Traceroute uses the fact that if a router normally sees a packet that it would be forced to put a zero value in TTL. For example, if there would be more than 64 hops in the internet, then you are a router, you receive a packet that has TTL, that has a hop limit. Sorry, I said TTL. TTL is the IPv4 term for this, which has a hop limit equal to 1, and you need to forward it. If it's for you, that's good. If you're the destination, you receive hop limit equal 1, everything's fine. But if you're a router and you need to forward it further, you will be forced to create a packet with hop limit equal 0. Then you can't, you kill the packet, and if you're a well-behaved router, you send an error message back to the source saying, I'm sorry, I had to kill your packet because the hop count was expired. Most routers do that, not all, but most. And this is exploited by Traceroute. When you use Traceroute to a given IP address, what Traceroute does is it sends a test packet, in fact a UDP test packet, to the destination with increasing TTLs. So first it will try TTL equal 1. If the destination is on link, the destination will get it and will respond. And that is the end of it. Traceroute will terminate, and you will know you are directly on link. You're on link with the destination. If the destination is not on link, the packet will be forwarded to the next router on your path to the destination, and the router will kill the packet and send you an ICMP error. And then you will discover who the first hop is. Then Traceroute will see this is an ICMP error and not the response. Therefore, it continues increasing the TTL. It'll try again with TTL equal 2. And then somebody who's 2 hops away from you will expire and send you an answer, etc., until you reach the destination. And sometimes at the destination, the program is a bit weird, like you've seen in some of the traces, where you've in fact reached the destination, but the destination, instead of responding with a reply saying, yes, here I am, it responds with an ICMP error message with a bogus error message, the one that we've printed with the non-existing names. So this is how Traceroute does, and the default is, as I said, 64 at the source. IPv4, so there are other fields in IPv6 header that we will describe later, in particular traffic class, flow label, that are in practice never used, and the payload length, which is the length which is used, which is the length of the of what is contained inside the IP packet. IPv4 is very similar, except the hop count, the hop limit is called time to live. When IP was done, believe it or not, it was truly a timestamp. So we said 2 seconds. This packet should not live more than 2 seconds, which would assume that every router would count how much time a packet spent inside the router and decrement this by the number of milliseconds spent inside the machine. Of course, if you can imagine now a giga packet per second router timestamping all the packets that go through it, that won't work. But that was the original idea. That's why it's called time to live. So it's not a time. It's really a hop limit. There are other fields that we'll discuss a bit later. So we have seen already IP packets. So you can see all those fields when you do Wireshark. This is an IPv4 packet. This is an IPv6 packet, which is again the same except it's longer. There are special fields like ECN, which are inside the type of service byte, that we will discuss a bit later when we discuss congestion control. But apart from that, the main fields, we've seen all of them. So a quick poll to wake you up. Here I'm alluding to this Wireshark trace here. I'm saying here is an Ethernet packet, Ethernet type saying it is IPv6. And here's the IPv6 packet. I see a number of things, among them a destination address and a source address. And the question is, yes, it works now. What is the destination MAC address of this packet? I propose some solutions. And if you try to be extremely smart, you can always find that none of those answers are probably correct, but don't be too smart. Just try to think of the obvious answer. Which one is it? The end of the sentence that he raised here, it's a solicited node multicast address. Right? This is what I could call a NARP packet. Right? But this guy is trying to acquire some some IP address. So it is sending to this, which is a multicast IP address. And now the question is, what is the MAC address that we see inside an IP packet that's sent to an IP multicast address? 5 more seconds. Two more seconds. Majority answer is the correct one. We haven't seen it, so this is we are peeking forward into the MAC layer module that I will start in a minute. So this is which MAC address could it be? It could be broadcast if some protocols do it, but it's not the broadcast address as you recognize it. So what is it? Well, it cannot be the MAC address of a given device because that would be completely stupid. I mean, you send to a multicast address, and the MAC address of a device is a unicast address. So if you put the MAC address of one machine, you send it to exactly this machine. So it defeats the purpose of having a multicast address. So what we're discovering here is that there are MAC layer multicast addresses as well. So the Ethernet switches, if they are expensive, they know and recognize those addresses, and they will also do distribution trees, as we will see for a bit later. So that is the answer to this question. Allez, one more. A host generates a packet with hop limit equal 1. Which of the answer do you prefer? A bridge is an Ethernet concentrator, an Ethernet box. Five more seconds. And the correct answer is 2. Wonderful. Hop limit equal 1 means the next router will kill this packet. Now the bridges, like the Ethernet concentrators, they don't see even the IP header, so they don't care in principle. They can always hack something to care, but in principle, this is why I say don't be too smart. If your bridge is not hacked, when it looks at the packet, it looks only at the Ethernet header. It's completely ignorant of IP. So of course, if it has to forward it, it will forward it. Voilà, that's the end of IP module 2. Of course, in the rest of the course, we'll come back to other features of IP that we haven't seen here.